Hello everyone, this is TSS Zindabad and today we are going to discuss the daily challenge of Leetcode. So the question is minimum falling path sum. Let's jump into the problem statement. We are given an into an array of integers matrix and we need to return minimum sum of any falling path through matrix. Now let's understand what is this falling path. Falling path starts at any element in the first row, chooses the element in the next row, and that is either directly below, diagonally left, or right. So basically, when we talk about the falling path, it is saying that you have to start. Your starting point can be any cell in the 0th row, right? And then that means if you were on I comma j, where I is equal to 0, right? Then you have three options. That means you can go from this one cell to three different places. First one being the left diagonal, right? Second being the cell just below it. And third is the right diagonal. So if I was at a cell I comma j, then if I go to the left diagonal, as I'm moving down, my row will increase, the row value, and my column value will decrease by 1. Then my cell just below it, again, as we're going to the next row, I plus 1 and j remains the same because it is just below, so the column remains the same. In the right diagonal, I go to the next row and my column value increases by 1. So this is how I can form a falling path in my matrix. And I want to form such a falling path in my matrix that eventually whatever I get is the minimum sum. Okay, so this is the problem statement. Let us assume this is an example that is given to me. So here, as you can see, this is the 0th row, right? So I can start from either cell 0, 0, 0, 1 or 0, 2. Right? It entirely depends upon me. I need to move in a way such that my final answer is giving me the minimum sum. So when we talk about that, I can go to any path, right? And when we're going to any path, we are figuring out all the possible ways. Then the first approach that should always come to your mind is recursion. Recursion helps us to explore all the possible ways. It says you just figure out the base case, rest is all up to you. So let's take this example and form an approach. Okay, so this is the example that I have. And so far I have established this fact that I'll be using something like recursion to solve this problem. So whenever we talk about recursion, we know recursion can be solved easily using 3 steps. First is forming a base case, right? Second is explore all possibilities. And third is make the recursive function. Okay, so these are the 3 steps that we need to follow when we are working with recursion. Okay, so I know that I am starting from my 0th row, right? So we'll come to the base case later. First, let's talk about the recursive function. Whenever we're talking about the recursive function, I know if I'm starting from my 0th row, I choose any of the elements. For example, I choose the element that is present at the index 0, 1, that is 1, right? So from 1, I can go to 3 possible places, right? So I've got 3 choices for each cell. We've already discussed that is the left diagonal, just a cell below it, or the right diagonal, right? So I have 3 choices, that is left diagonal, the below cell, and the right diagonal. So I can see that if I was on I comma j and this was my recursive function that was going on, in case of left, as we've discussed just above, I'll go to the next row and the j minus 1 column, and in case of below cell, I'll go down because I am moving forward, right? My column remains the same because we are still at the same column. right? And in case of right diagonal, I'll move one column further and my column value, my row value and column value both increases, right? So I understand that if I was on the 0th row, I choose one element satisfying the minimum criteria that I want to, which is being handled by recursion, and it has three choices. Now let us suppose through any XYZ operations, recursion figured out that I should go to 4. That is the best possible choice I have. Then again from 4, I can have three choices, right? Now, when we talk about this, we understand that these all are recursive functions. So this formulates our recursive function. We're done with step 3. Now, what is the step 2? It was about exploring all the possibilities. What is the possibility? Whenever we talk about the possibility, we need to understand what is the target. So in this question, the target is to find the minimum, right? So what I'll do is, whatever I have got the result for all three of these, I'll simply take a minimum of all three values and I'll have the final answer. Now let's talk about the base case. See, whenever we are talking about the base case, it is very important for you to remember that base case is always with respect to the parameters which are changing, right? So it helps you understand that which cases might lead to certain edge cases or be a termination point for your recursion. Okay, so first here let's talk about what are the edge cases I need to handle. Now, what are edge cases? Edge cases are particularly the cases that if you will handle, you will not get something like a runtime error. Why? Why do we get this runtime error? We get it when we are going to a position which is not present in our memory, right? For example, in this matrix, which is a 3 cross 3 matrix, I say you go to -1, 0. That means go to -1 row and 0th column. And also that's not possible, right? Similarly, here if I ask you to go to 2, 3, we do not have a third column. We do not have a column index 3. We do not have the fourth column, right? As we know, matrix, arrays, all these data structures start from 0 index, right? So we need to handle this edge cases. Now, what I can see here is that, okay, I'll go to, for handling these edge cases, I'll go to my recursive call that I've just figured out that these recursive calls would be made, right? I see here that my J, first of all, let's see, the J value is continuously changing, right? As soon as it is only J, it is okay. I do not have to worry a lot. But if you look at J minus 1, so, there needs to be a check that J should never be less than 0. Because if J is less than 0, that means it is not the index within the dimensions of the matrix, right? So in that case, what we'll do, we'll simply return something like a very big number, 1E9. Why am I returning 1E9? Why am I not returning any other number? That is because, guys, we have to find the minimum falling path, right? If you return something as a 0, it might affect your actual answer, which should be computed, right? And why am I not using something like an int max? Is basically it prevents, like basically if you use that, there might be a chance of integer overflow, but with 1E9, it's like handled. Then talking about here, we see that the value of the column j plus 1, it might keep on increasing, right? Maximum possible value that for this particular example, 3 cross 3 matrix I can have is the column value that is 2. But suppose j's value was 2, then 2 plus 1 becomes 3. It is making a call where there is no element present in my memory, right? That will lead to a runtime error. So I need to say that if j becomes greater than or equal to n assuming the number of columns, right? Then also you will return the same 1E9 as the value so that we get a very maximum answer, so that it never becomes the minimum possible answer that is required for the question. I hope this is clear. We've talked about the edge case. Now let's talk about what termination point should we have. So I see, as I told you initially, whenever you're talking about the base cases, you need to talk about the parameters which are changing. So coming back again to the recursive function, I have handled the j minus 1 condition, the j plus 1 condition, right? Both of them with respect to the column values. But I also see that I have something like I, which corresponds to the row. So if I am starting from the 0th row, I will eventually end when I reach the last row. So I'll say if at any point of time, my integer I becomes equal to n minus 1, which is the last row in the matrix. In that case, what you need to return me is return me whatever value is present on that index, right? And that's it. This is the recursive approach that we need to follow, right? Here I have talked about exactly the way the question has asked me, that is considering that I am starting from the 0th row and I'm going down and finally terminating at my last row. There's one more thing that you can do, what I will be following, particularly for solving this question. What I will be doing is, let me quickly copy paste it here. What I'll be doing is very, very subtle change. I'll say I am starting from my last row, right? And I'll be terminating at my 0th row. So I am just simply changing the starting and the termination point for my matrix. Now, how will it affect it? It will affect it in the terms of the recursive function parameters. As earlier, what we were doing is we were going down, but now we'll be going up. That means I can initially start from the last row, any column, right? It can be 7, 8, 9, which I'm starting with, satisfying my minimum criteria, right? So if I am on ij, then I have to go to either the upper left diagonal. In this case, the value of I will decrement, but the column values which we have talked about remain the same, right? Or we can go to the upper cell, that is I minus 1 and column remains the same, or we can go to the upper right diagonal. Here, my row value decreases and the column value increases, right? And for this, my edge case with respect to j, as you see, we have not changed the value of j here, right? It remains what it was in the previous also when I was starting from the 0th row and ending at the last row. So it remains the same. But when you talk about the termination case, where I want to terminate it, then initially what I was doing it, that if my integer I becomes equal to the last row, here what I'll do is, because I'm starting from the last row, I'll have something like I is equal to 0, then return me whatever is present at the 0th row and whichever corresponding column I am on. So it's a very, very simple change. You can do any one of them. I feel this to be a bit easier. So, okay. Now let's quickly code this up. Then we'll talk about the time and space complexity and how we can optimize it. Okay, guys. So this is the problem statement. What I'll do is I'll quickly create something like int mini and I'll initialize it with a very big value. And then because I can have any starting point, right? And I'm starting from the last row. So I can say that if I can consider, let's first of all make an integer n corresponding to the size of the matrix so that I don't have to write it again and again. So here I'll simply say that change mini accordingly, right? Let's call a solve function in which I'll give the row value as n minus 1. That's the last row because we know this is an n cross n matrix, right? And the column value as j in the loop that is we are running. And we'll pass the 2D matrix and we'll simply return the mini. Now let's quickly create a solve function that's of integer type. It is getting a row value, it is getting a column value, and it is getting a 2D vector, right? Okay, so here, first let's build first of all, as we know that we have the edge cases, right? Then after the edge cases, we'll have the termination case. Then we can have something like the recursive function. So first of all, let's code up the recursive function. We'll say that let's have something like int upper left diagonal. In this, what I am saying is whatever is the value of matrix ij, that means wherever you are standing, take that into your sum and then move to the upper left diagonal. That means my row value decreases by 1 and my column value also decreases by 1, and we'll simply pass the 2D matrix. The other possible choice I have is going to the upper cell, right? So I'll just write upper. In this also, what you can do is I'll copy paste condition so that we can just have to change the parameters. So here I'll say take that value where you're standing, take that value for that cell. Now for moving forward, call the solve function, go one row up, and as we are just going one cell up, the column remains the same. Then let's have the upper right diagonal, and here also I'll say take whatever the matrix is holding for present I and j value, call the solve function, we'll go one row up, but as now we are going to the right side, we'll have a +1 in the column value. And now let's talk about exploring all possibilities. Here I'll simply return whatever is the minimum of all three values, right? So I'll quickly code it up. Okay, now let's talk about the edge cases. As we know, the possible edge cases will be with respect to the column value. So what I'll say is, I'll say, okay, let's have if j is less than 0 or j is greater than equal to matrix dot size, right? In that case, return a very big value, 1e9. Talking about the termination case, I'll say if at any point of time, that means my row value becomes 0. That means I've reached the 0th row from my last row. Then return me whatever is present at that particular cell. I think we are good to go. Let's quickly run this. Okay, let's submit it. And I'm probably will get a TLE. That is because it is taking a lot of time complexity. Yes, we got a TLE. Okay, let's quickly copy paste this code and talk about the time and space complexity. And then, okay, so looking at this code, we know the one thing that for every cell, there are n into n cells in my matrix, right? For every cell, I have 3 choices. So it makes my time complexity O of n square into 3 raised to the power n. Why? Because I have, for every cell in my matrix, I have these 3 choices that I have to explore to get the minimum right answer. Okay, so it is a very, very big time complexity, exponential in nature. And talking about the space complexity, in the worst case scenario, we can have a space complexity of O of n. That is because we'll have a recursion stack space that will be created. So to understand the time and space complexity and why it is this way, let's quickly take an example and I'll quickly do a dry run for it so that you understand how this time and space complexity is being achieved. Then we'll talk about optimizing it. Okay, so this is the code that we have done for recursion, and let's take this as the example. So I'll create a tree, the recursion tree, as well as I'll also be maintaining a recursion stack space. So initially I have a mini that is 1e9, right? I'll say, okay, let the value of j is 0. So the first solve function is called, and it is saying that you go to n minus 1, considering this is a 3 into 3 matrix. So I go to row number 2, column number j is 0, so 0, right? This is added into my recursion stack space. So here I get a call of s2, 0 and my pointer is pointing to it. I go to my solve function. There I see that no, the edge case is not being satisfied because my j is not less than 0. It is neither greater than equal to the size of n, right? And I is also not equal to 0. So it is not a termination case. I come to this line. Here, what I'll say is whatever is present in matrix I comma j, what is I comma j? It is 2 comma 0. So here you can see that at 2 comma 0, we have 7. So I'll say, okay, have 7 plus call another solve function. Therein I minus 1, we had 2 in case of I. So we'll have 1 and j is also decremented. So it becomes minus 1. So now we move into this section. As soon as we come here, this is added into a recursion stack space. And now my pointer is pointing to this function. As soon as this function comes into execution, we see that yeah, edge case is valid here because the value of j has become less than 0. So in this case, what I do is I say just return 1e9. So now this is returning 1e9 and plus 7, something like this it is returning. And as soon as it has returned, we'll pop it out from the stack. And again, my pointer is pointing towards the function 2 comma 0. Now here, the next call is made. Here what it says is, it says go take whatever is in matrix I comma j, that is again 7 because 2 comma 0 had 7, and have a function solve in which what you are doing is you are saying that go to the I minus 1 row, that is 2 minus 1 is 1, and the column remains the same. So this function call is added into my recursion stack space. Here my pointer goes to this and I'm executing it. I check that none of the edge cases are satisfying, neither is the termination case. So what I say is, I say, okay, let's go to this part of the code. Now here again, I'll say whatever is present on the index I comma 0. So I see on I comma 0, we have got a 6. So I say for this call, have 6 plus call the solve function wherein you passing the parameters, whatever is the value of I decremented by 1, you make it 0. Whatever is the value of j decremented by 1, you get a minus 1, right? This is added into the recursion stack space. I get s0 comma minus 1. Now my pointer is pointing towards this. As soon as this is executed, I see that the value of j is less than 0. It is satisfying the edge case. So it will return 1e9. So now this function is returning 1e9 plus 6 and it has been popped out from my stack. And again, my pointer is pointing towards the function which had parameter 1 comma 0, right? It has executed this line. It goes to the next line here for the upper int upper. So what it says is, okay, now let's have another recursion call. I'm drawing it here. It says whatever is at the value at matrix 1 comma 0, which is 6, and call the solve function wherein you decrement the row value by 1, it becomes 0 and the j value remains the same. Okay, so here, as you can see, when we do that, we'll add a function in the recursion stack space, that is s0 comma 0, and for that, we'll come to the solve function. As soon as we come to the solve function, we see that the edge case is not being satisfied, but the termination case is being satisfied. What is the termination case? That I has become 0, and that is true. In that case, I need to return whatever is the value, and that is 2. So I'll say 6 plus 2, that is 8. Hence, 8 is returned to this function from this call. So this gets popped out, and we are again on the function that is which had parameter 1 comma 0. That means I'll change the pointer for you guys. I am here again, right? Now what happens is I'll say, okay, I have also completed this line segment. Now let's figure out upper right diagonal. So another call is made. I'll make it here. That will have whatever is present on matrix 1 comma 0, that is 6, plus call the solve function wherein you are decrementing the row value, that is making it 0, and you're incrementing the column value, that is 1. So this is added into my recursion stack space, that is s0 comma 1. Now my pointer is pointing towards this. As soon as my pointer is pointing towards this, I see this is again a termination case. Why? Because I has become 0. So in this case, you see 0 comma 1 is 1. It will say 1. So 6 plus 1 becomes 7. So this is returning 7. Okay. So this pops out. As soon as this pops out, we know that S1 comma 0 has also completed all the line segments. So it will go to the return statement and it will say return me the minimum value to its parent. So to its parent, it will return, because see, from its first child for function which had the parameter 1 comma 0, from the upper left diagonal we had something like 189, from the upper we had 8, from the upper right diagonal we had 7. So the minimum turns out to be 7, it will return 7. Okay, so after that this has been popped out, and again my pointer is pointing towards s2 comma 0. Now my s2 comma 0 has worked with upper left diagonal and upper with respect to it. Now it will work on the upper right diagonal. So what happens is it will say, okay, what you should do is you should take whatever is there in the matrix 2 comma 0, which is 7, and make a call for solve, that is I minus 1, that makes it 1, and j plus 1, that makes it 1. So I am somewhere here 5, that is at the index value of 1 comma 1. So now this call is added into the recursion stack space, that is s1 comma 1, and my pointer is pointing towards it. As soon as we come here on s1 comma 1, what I see is that it is not satisfying either the edge case or the termination case. So we again run all these functions and we figure it out. I'll not be drawing the complete recursion tree and the recursion stack space for you because it's very, very lengthy. For us to understand how we can optimize this code further, I'll quickly do one thing, that I'll make a tree for you so that you know how many calls are being made and how we can figure out what optimization technique can be applied for it. Okay, so here you can see one thing, that as I have already told you how the recursion tree and the recursion stack space is being developed, and that was just for one, and we did not even complete it. We have 3 more cells from which it had to be done. So let's quickly, considering that I am starting from something like 0 comma 0, right? So as I'm starting from the last one, so that is 2 comma 0. From this, I can either go to this direction, this direction, this direction, that is upper left diagonal, upper or right. As considering the upper left is going out of the bound, not considering it, so I can either go to s1 comma 0 or I can go to s1 comma 1. This section would only be computed when this is done, right? I'm just drawing it for you to understand how we are going to figure out the pattern in it. As soon as it comes to s1 comma 0, which is here, it can again go to 3 different places. So it can go to s0 comma 0 or s0 comma 1, right? So again, this part will be solved only when this is solved. So for example, I've come here, as I've reached the termination point, that is okay. I've come here, I've again reached the termination point, I'll not go any further. So let's talk about s1 comma 1. That means if I had from 7, I had chosen something like 5, then I would have had these 3 options. So which would have been something like s0 comma 0, s0 comma 1, s0 comma 2. Now here you can see that we are recomputing s0 comma 0, s0 comma 0, s0 comma 1, s0 comma 1, and that is also for just s2 comma 0. I have to still compute something like s2 comma 1, s2 comma 2, s being my recursive function, and this is the row value and the column value. So you can think of how many overlapping sub-problems it has, right? So whenever we have overlapping subproblems in the case of recursion, the solution to it is dynamic programming. So what does dynamic programming do? It says that if you have once computed something, right? You have computed something, then what you do, you store it at a place, right? You store it here, and these are the lines of code. So for example, I've computed the value of A, I'll store it here, and here also I'm figuring out the value of A somewhere, right? And again, I need the value of A rather than figuring it out and having a huge time complexity, use it directly, right? So this is what dynamic programming does. Now let's talk about how it does it and what changes do we need to make in our code and which further time complexity and space complexity will be achieved after doing. Okay, so guys, this was the code that we had written for recursion. Now let's convert this code into a dynamic programming code, that is memoization. Memoization is a top-down approach, right? So what I'll do is I'll simply create a 2D DP vector, right? The size of it depends upon the number of parameters that are changing in the recursion function, changing in the recursive function, right? So as I see that the value of I and j is changing, so it will be a 2D DP vector, right? I'll add it here. And what I'll do is I'll simply add a condition that if at any point of time the DP 2D DP I comma j value is not equal to -1. We can initialize it with -1. It denotes that that cell has not been computed yet. Okay. So it says that if it is not -1, that means it has already been computed. So you do not need to recompute it. In that case, what you will do is you will simply return me whatever you have stored in your DP I comma j value, right? And you can simply add DP here and here and here. And whatever you're finding every time for with respect to I comma j, as you saw in the recursion we were doing, we'll simply store it in this 2D vector, right? So when we do this, the time complexity, which was earlier exponential, it boils down to O of n square. Why? Because we're saving things and we're reusing the saved stuff rather than recomputing it. And now the space complexity becomes O of n square. That is because we are having a DP vector, right? So let's quickly code this approach up. So this was the code that I had done so far. What I'll do is I'll quickly make a 2D vector. I'll name it DP. It is of size n cross n, and we'll initialize it with -1, right? We'll pass it to the solve function. Let's pass it here also. And I'll add a function here. Let's add a comment that this is memoization. So what I'll do is I'll say if dp of I j is not equal to -1, in that case you return me dp of I j, and here also in the recursive call add dp, and when finally you're computing it for any ij value, store it correspondingly so that you are not recomputing it. I think we're good to go. Let's run. It is working fine, but on submitting, I don't feel it will work because the space complexity of is O of n square and the time complexity is also of n square. So let's see if it works. Okay, we got a time limit exceeded. So now we have this code. I'll quickly copy paste this code. So this is the DP memoization code. Okay. And we know that its time complexity is O of n square and its space complexity is also O of n square. Now I have this code. How can I further optimize it so that it gets actually accepted? Because see, we cannot reduce the time complexity any further. We have significantly reduced it, right? And as we have a 2D vector, so we have to work with a time complexity that is O of n square. But we can do something with respect to the space complexity. So let's understand what we can do. As we already have the memoization solution, we can move forward to something known as tabulation. Now, what does tabulation do? It says that you have already worked with a top-down approach. Memoization is a top-down approach, and tabulation is a bottom-up approach. So it says whatever you've considered as your base cases, including the edge cases, you simply convert it into a bottom-up approach. That means begin from the base and start building upon, right? So here, what I'll do is I'll again have something like a 2D vector DP, right? Which is of n into n size, and it is initialized with 0 this time. So here what I'll say is that, okay, you've been initialized with 0. Alongside that, what I want you to do is that, first of all, let's figure out, we know that at any point of time, if you reach this particular condition, oh, I'm sorry. So we know that if you reach at this particular condition, that is a termination case, right? You will get the particular value of the matrix. So what I can say is I'll simply run a for loop for running from all the columns, right? And I'll say that in my DP 0, j, right? What you will do is you will simply put whatever is in matrix 0, j. Because see, this is right here. We are just simply converting the memoization, the top-down approach to bottom-up, right? Why am I converting into bottom-up is something you'll realize when I'll further optimize using space optimization, right? So I have said that do this. So that means I filled my DT vector. I had a 2D vector, something like this, right? So I'm saying that, okay, for whatever is the value of the initial matrix that you've given, fill it for each of the columns for my zeroth row. So considering the previous example, we had 2, 1, 3, right? So it will simply fill here 2, 1, 3 after this for loop. Then it says now build the TP table iteratively. First we were doing it through recursion. Now we'll simply for tabulation, we'll have something like iteration. So here now as we worked with I is equals to 0, so my for loop, we'll have two for loops. First one would be for the number of rows. So I'll say it will go from 1 to n, and my second one will go from 0 to n, right? And here I have to do nothing new. I have to simply copy paste these here. How I'll do that is I'll say, see, if you are the int upper, that means you are the cell just above the cell I'm standing on, right? In that case, you just have to, now, first we were calling a recursive call, right? Now we're not calling a recursive call. I'll say go to dp I minus 1 comma j. That means for that, you have to take the value of the dp, my vector dp, 2d dp, taking a value I minus 1. That means if I was 1, then take dp 0 and whatever is the value of j, right? Then talking about in the case of what we have to do is, see, in the memoization code, what we were doing is we were having something like an edge case where we were figuring out if the value of j at any point of time goes out of bound. So here in iterative code, we have to do it explicitly. So I'll say initially assume that my upper left diagonal is equals to 1e9 and my upper right diagonal is also equal to 1e9. Okay. Then I'll say that if the value of j is greater than 0, right? If it is greater than 0 only, then I can go to the upper left diagonal because my j is at max what? It is 1, right? So 1 minus 1 will be 0, and that is in the bound I can go to, right? So here I'll say then in that case, you make my upper left diagonal dp I minus 1 j minus 1. How we know this I minus 1 j minus 1? Guys, it is right here, right? Look at these solve functions here. It is right here. I'm just copy pasting the code into a different approach. That means first we were having something like a top down. Now we're working with bottom up approach, right? So now for the case of upper right, I'll say if j is less than n minus 1, right? In that case, I'll say upper right diagonal is equals to dp I minus 1 and j plus 1. And what I can eventually do is, we saw that we were returning here, right? So I can simply store dp I comma j, which will be equal to what? It will be equal to whatever is the value of matrix I comma j. Guys, you saw we have to take whatever we are standing on also, and whatever is the minimum for all these three values that have computed, right? And then finally, after doing this, I'll return. See, now what happens is, after doing this, I know something that I have a DT vector which is storing my answer, right? So this is filled, this was initially filled by me, right? Then this was computed using this. Then the second row is computed using the first row. Eventually, for this example, as it is a 3 into 3 matrix, right? As it is a 3 into 3 matrix, my last row will have the answer for the dp to d vector. So now to get the final answer, I have to iterate over this. So I can simply iterate over the last row, right? I can have something like mini that is giving me the minimum of whatever is present on dp n minus 1 and the g value continues to change. And we'll simply return a mean. The time and space complexity remains O of n square both, but this approach is very important for you to understand because this makes us go to our very next approach, which will be accepted, which is space optimization. Now, what does space optimization says? It says that, do you see one thing? There is a pattern. Here, when you were talking about everything, did you realize I'm talking about a pattern that I have this 3D matrix dp in which this is already stored by me. I'm already writing something like 217. This is already there initially. Using this, using this value, I'm computing my first row, right? And then I'll have my first row, let us assume I got something like 5, 4, 6, right? Then using the first row, I'll be computing my second row and so on. So I can notice one thing that at any point of time, I do not require whole of the DP. I just require the row above the one I'm trying to compute, right? And eventually the answer would be in the last row itself, right? So I can lead to, this approach will lead to a space complexity of O of n, and the time complexity will remain to be O of n square. Now we've understood that for computing one row, I just need the row that is just above it, right? I do not need to store whole dp vector that is O of n square. I don't need to do that. I can simply achieve it using something very simple, which is a vector, a previous vector, right? So I can have a space optimization by having two vectors. One can be the previous vector and the other can be the current vector. And then I can make my previous vector is equals to the current vector. And I'll have the answer eventually, right? And further you will see that your previous vector only will be storing the answer because you converted the current into previous, right? Even for the last one. So using two vectors only from a time and space complexity so high to boiling it down to so low. This is a thought process you need to understand and implement. Okay. So now what I'll do is, first let's quickly code this up. First let's have the code from memoization be converted into tabulation. And then we'll talk about converting into space optimization in the code editor. Then we'll talk about how that is done. I'll quickly do a dry run for you people so that you understand how the space optimization works accordingly. Say. Okay, so this was the memoization code. I'll quickly comment this all out because I don't need it anymore, right? And let's keep mini. We need this. I'll quickly I'll quickly comment this out and let's make it 0. It's just storing a value 0. Then what I'll do is I'll say okay, let's run a for loop, which is basically me iterating over all the possible values of my column, right? And I am just storing it for my 0th row and different columns corresponding to it. So I have formed the foundation, that means the base from where I am giving it one previous to compute the current, right? Now I'll run another for loop for building the DP table in the iterative manner. So I will start from 1 because I've already worked with I is equals to 0 case. I'll say, let's create 2 for loops, right? And my j goes from 0 to n. Now here, what I am doing is, I'll quickly copy paste these here so that you know how I'm converting it, right? So let's put it here and let's uncomment these. Yeah. So here what I'll do is, I know this one thing, that when you talk about int upper, it can be done easily, right? Now here what will happen is, just my solve function will be converted into TP, and the indexes that have been provided, those remain the same. So that means I will be working with I-1 and j, right? Now talking about the int upper left diagonal and right diagonal, what I'll do is, I'll quickly say that take this int upper right diagonal, put it here, initialize it with 1e9. Similarly, take this int upper left diagonal and initialize it with 1e9 also. Now you can go to the right diagonal if the value of j is less than n minus 1, right? And you can update the value of upper left diagonal only if the value of j is greater than 0, right? Here, let's keep matrix I comma j as it is. My solve gets converted into TP. It's either just very subtle changes. I'm converting an approach which was top down to bottom up, right? And we'll delete all of it. Here also, I'll have something like TP. We'll add these braces here for the 2D vector. And now what I need to do is, by doing all of this, my DP vector is ready. Now I know that my DP vector's last row has the answer. So what I'll say is, I'll say for int j is equals to 0, j is less than n, j plus plus, right? Compare and give me the minimum, right? So it will say dp n minus 1 j. Okay, n minus 1 and j, and then we can return the mean. Let's run it. Okay, I have not put semicolon somewhere here. Okay. Okay, yeah. This is one more thing that I have not done. I have to put dp I comma j equals to the minimum, upper, minimum, upper RD. Compare it with the code that we just did. It is exactly same, just very, very minute differences. That was something a recursive call. This is an iterative code. And okay, it is having an int again. We don't need that. Okay, some little typos. I'm sorry. Yeah, we're good to go. I think we'll still get a TLE. Okay, though this worked, right? But still, let's further space optimize it. Now, as I've told you, that what is happening is I'm storing a 2D DP. And I know that I don't need the 2D DP, I just need the previous vector to compute the current. So what I'll do is, I'll quickly comment all of this code out, right? So that we know what we are doing and how we are achieving O of n space complexity. Let's quickly comment all of this out. And let's just move it somewhere down. Yeah, here. So now what I have thought of is, I'll say, okay, now I'll just create two vectors and I'll be working with just two vectors. I'll not have a 2D vector. I'll have just one vector of space n. So I'll say, let's create a vector int. Okay, vector int. Let's name it previous, and it is of size n, and it has everything initialized to 0. we will run a for loop for j is equals to 0, j is less than n j plus plus, and we'll say put previous j is equals to whatever is matrix 0 in matrix 0 row and jth whole column, right? So that means what I was doing first, I was creating in my tabulation solution, what I was doing was I was doing the very same thing, but I was doing it for the 2D vector. Why? By keeping the similar thing, right? Now what I am doing here is I'm creating a very different vector, and I'm creating one being previous, which is storing the initial base that I've given to it, that okay, you have this initial previous. Now compute me the current, then convert the current into previous, and keep and keep computing me the currents. Okay, so now I'll say I'll have a for loop for int I is equals to 1, I is less than n, I plus plus. It's a very similar loop to what we had. So int j is equals to 0, j is less than n, j plus plus. Now, before moving further, what I'll do is I'll create a vector current, which will be created every time I go to the other row, right? So I'm creating a current vector of size n, and it is initialized to 0. I'm going to the here when I enter the for loop for j, now I can access both of them, and I do not have to do anything different now. What I'll do is I'll simply copy paste this, the one that we have previously written for tabulation, and we'll make the changes in it. Let's quickly comment this out. Let's quickly uncomment this. So now what I'll do is I'll say that, yeah, I know this one thing. What I have to do is that my upper remains the same as it was. I've initialized my upper right diagonal and upper left diagonal to 1A9. And now what I'll say is my upper left or upper right diagonal, rather than having dp I minus 1 j plus 1, in the case of upper right diagonal, I'll have something like dp I minus 1 now corresponds to previous. So I'll make it previous. And for j minus 1, dp I minus 1 again corresponds to previous. Then eventually I'll say in the place of dpi, I'll say current I. That means the current vector I'm working on its jth index, you put the minimum, and then we are here converting the previous into the current. Then similarly, again, as we had this for loop, we'll be using the same code up there for space optimization. I'll quickly uncomment it. Here, rather than dp of n minus 1, what should I write? I should write simply previous. It is acting as my dp. Now, let's submit it. Okay, it says I do not have a dp. We're on line 35. Okay, yeah. Even here, when we're talking about the upper one, we need to convert dp I minus 1 to previous, because now dp I minus 1 has become that. What was dp I minus 1? That was the row in my 2D dp matrix that is just above the one I am going to compute. That has already been computed, and it works completely fine. Now, let's quickly talk about the time and space complexity and do a dry run. Okay, so this is the space optimized code that we have written, and its time complexity is O of n square and its space complexity is O of n. It is O of n because every time we have a previous vector that is of n, current vector that is of n, and the time complexity of O of n square because of this loop. Now I'll quickly have a dry run. What I'm doing is I'll create a previous vector. So I know that n is equals to 3. So I have this previous vector here, 0, 1, 2. I say that go to matrix 0, comma j, that means 0 through and all the columns, and just put it in whatever is the value in previous. So I get something like this from this for loop. Then I come to this. here I'll be running it. That means let's quickly have something like I and j so that we can keep a track. And we have got a cur that is again of the same size, that is n. It is initialized to 0 initially. So what I am doing is I is 1, j is 0. That means I am somewhere here. First row, 0th column, right? So what I am saying is, for if you are here, what you have to do is, if you want to find int upper, right? So add matrix I comma j. What is matrix I comma j? 1 comma 0. So one matrix 1 comma 0 is 6 plus previous j. What is the value of j? 0. So what is previous 0? That is 2. And similarly, if you look at how recursion, tabulation, all of this was working, we were going like this only. If I have to go to the upper cell, this needs to be the upper cell, and see, this is the upper cell. So I get a 8 in this condition in case of upper, right? Then I'll say make upper right diagonal as 1e9, and similarly make the upper left diagonal also as 1e9. Then you'll say that if j is less than n minus 1, we can say that yes, it is. So you can compute the upper right diagonal. It gets converted into 6 plus what is previous j plus 1. So j plus 1 becomes 1, previous 1 becomes 1. So we get a 7. Then we say that if j is greater than 0, we say no, it is not. So this will not be computed. So now my current j, that means current 0 index will have the minimum of all of this, and we get 7 as the minimum. So 7 comes here, right? After that, as we've computed it, now what we are going to do is we are going to we have worked with j is equals to 0. Now j gets incremented, j becomes 1. So now I'm working with 1 comma 1. So when I'm working with 1 comma 1, okay. So now I am on 1 comma 1 here, right? So this is 1 comma 1. Now what happens is, I will say let's compute the upper for this. So my upper becomes 5 plus previous j. Previous, now j's value is 1, so previous j is 1, so it becomes 6. Then I'll say that both make upper right diagonal 1e9 and upper left diagonal also as 1e9. It is okay. Then I say that is j less than n minus 1? It would say yes, it is 1, so it is less than 2. So yeah, you can go for upper right diagonal. So here it becomes 5 plus previous j plus 1. J was 1, j plus 1 becomes 2, so it is 3. So 3 becomes 8. Then we will say that is j greater than 0? It is, because it is 1. So we can also compute upper left diagonal. It becomes 5 plus previous j minus 1. J's value was 1, j minus 1 becomes 0, that is 2. So that is 7. So we get 6, 8, 7. And then we have to compute the minimum. When we compute the minimum, we get a 6. So on current j's value was 1, current 1, we'll put 6, right? Similarly, the value of j, similarly now the value of j gets updated to 2, right? Then we come here, we've created, we come here, we'll say, okay, we have upper. Now upper will be 1, 2. Matrix 1 comma 2 is 4. So we say 4 plus what you will say previous j. Previous of j is, that means j is 2. So previous of j here, if you see, it becomes 3. So it is 7. Then we'll have again an upper right diagonal, that is 1e9, and upper left diagonal, that is also 1e9. Then I'll say that as the value of j is not less than n minus 1, so I'll not recompute this. Let's go to upper left diagonal. As it is, its value is greater than 0, so we can work with it. It will become 4 plus previous j minus 1. Previous, the value of j was 2, 2 minus 1 becomes 1. Previous of 1 is 1, so it becomes 5. We take the minimum, it turns out to be 5, and it is added here. So I have computed current from my previous. Now in this line, it gets interchanged, and further I'll compute the rest of the rows that are remaining, and in the last row I'll get my answer. So this was the question. Thank you for viewing the video till the end. Please like, share, and subscribe.